Hi class, we are now on 7.3b. This is the mole concept in balanced equations. In the previous lessons, we introduced the concept of the mole, and we saw how we can use the mole concept with balanced equations. Using the coefficients from a balanced equation, we can relate the amount in moles of one substance in a balanced equation to the amounts of all the other substances consumed or produced in the reaction. In this lesson, we're going to expand on this idea. We'll look at one very common type of problem and explore the strategies for simplifying this type of calculation. So what about the coefficients? What does this mean? Let's break this down. You have 1 mole of iron. There are 2 moles of hydrochloric acid, 1 mole of iron 2 chloride, and 1 mole of hydrogen gas. Okay, one important type of stoichiometry calculation is the gram-to-gram problem. In this type of problem, we are given the mass of one reagent or product in grams and asked to find the mass of another reagent or product also in grams. To solve this problem, we must first convert the grams of a substance A into moles of A. We then relate the moles of substance A to the moles of substance B, using the mole ratio from the balanced equation. Finally, we can convert moles of B to grams of B using the molar mass. So basically, when we have a gram-to-gram problem, you can't just go from grams to grams. You have to get from grams to moles, then the ratio between these, and then back to grams in whatever the substance of B is using the molar mass. Let's look at an example. When heated with a Bunsen burner, magnesium carbonate decomposes to magnesium oxide and carbon dioxide, as shown in this equation. If 5.24 grams of magnesium carbonate are heated in this manner, how many grams of magnesium oxide can be produced? So what is this asking? This is asking that we start with 5.24 grams of magnesium carbonate, and it's heated. It then decomposes to magnesium oxide and CO2. So if we have this amount, it's asking how many grams of magnesium oxide were produced. So we first must convert the grams of magnesium carbonate to moles of magnesium carbonate. Then we relate these moles to magnesium oxide and then convert to grams of magnesium oxide. We begin with the 5.24 grams and we convert to moles of magnesium carbonate. We then multiply by 1 mole of magnesium carbonate over 84.32 grams of magnesium carbonate, which is the molar mass. The grams of magnesium carbonate cancel. We then convert to moles of magnesium oxide using the ratio in the balanced equation. 1 mole of magnesium oxide per 1 mole of magnesium carbonate. The moles of magnesium carbonate cancel. Finally, we convert to grams of magnesium oxide using the molar mass, 40.31 grams of magnesium oxide per 1 mole of magnesium oxide. The moles of magnesium oxide cancel. This gives us an answer of 2.51 grams of magnesium oxide. So basically, if you do this right and set it up, you can cancel this units with this units, leaving moles. Then we cancel out the moles using the ratio between these. Then from there, we get the moles. We use the molar mass, and that leaves us with our answer in grams, which is what we wanted. Okay, for many people, stoichiometry, I don't know why I can't say it right. Problems can seem overwhelming, but we will do a lot of this. You will learn this if you keep it up. The key to solving these problems is to recognize the simple patterns. Follow the patterns every time. All of the stoichiometry problems that we've done so far rely on just 3 types of conversions, each with its own conversion factor. So if we need to convert between grams and moles of one substance, we use the molar mass. If we need to convert between grams and particles of one substance, we use Avogadro's number. If we need to convert between 2 different substances, we use the mole ratio from the balanced equation. And pretty much this sums up everything that we're going to be doing. No matter how complicated the problems are, these are the conversions that we will always use. It will be one of these 3. Okay, so stoichiometry problems provide the amount of one compound, A, and ask us to relate this to the amount of another compound, B. These compounds can be solved by using the mole map, shown here. Like any map, this guide helps us to locate where we are going, and how to get there. For example, how do we get from grams of compound A to particles of compound B? Looking at the mole map, we can see that this requires 3 steps. Beginning with grams A, we must convert to moles of A, then to moles of B, and finally to particles of B. Okay, so let's put this into action. Zinc metal reacts with aqueous copper 2 chloride as shown in the equation. If 3.03 times 10 to the 21 atoms of zinc react, how many grams of zinc chloride will form? Show the sequence of conversions necessary and then calculate the numerical answer. So this question gives us the number of atoms of zinc. It asks us how many grams of zinc chloride will form. From the mole map, we can see that we are given particles of one species. Let's call it particles of A. We're asked for grams of another species. That's grams of B. From the mole map, we see that we must go particles of A to moles of A to moles of B to grams of B. So this means that we must go from atoms of zinc to moles of zinc chloride to grams of zinc chloride. Hopefully that makes sense and we can follow all of this and it's pretty clearly understood. And if not, take a look at it more and more. If it's still not connecting, let's go over it. Okay, so now that there's a strategy in place, and this is pretty much, regardless of the problem, if you do a mole map, you should be able, I call them like stepping stones, and that should allow you to understand how you get from one to the other, and then you can plug in the information. Okay, so we begin with 3.03 times 10 to the 21 atoms of zinc. We then convert to moles of zinc. We have to use Avogadro's number to do that. We multiply by 1 mole of zinc over 6.02 times 10 to the 23 atoms of zinc. The atoms of zinc then cancel. That's what we're doing right here. Next, we convert to moles of zinc chloride, which is here, so we can cancel out the moles of zinc. From the balanced equation, we can see that we form 1 mole of zinc chloride for every 1 mole of zinc. The moles of zinc cancel. Finally, we convert to grams of zinc chloride. To do this, we multiply by the formula mass of zinc chloride. 136.28 grams of zinc chloride over 1 mole of zinc chloride. The moles of zinc chloride cancel. This gives us a final answer of 0.686 grams of zinc chloride. That's 3 sig figs. Okay, to summarize, we can use the mole map like the one here to solve any stoichiometry problem that relates to grams, moles, and particles. Notice that we have only 3 types of conversion factors for these problems: the molar mass, Avogadro's number, and the mole ratio. That is the coefficients from the balanced equation. And they really don't change, so you will do the same steps over and over regardless of what the problem is. You just have to be comfortable to pull that information out. So let's start looking at some problems. In this reaction, how many moles of phosphorus trichloride will form from 45.0 moles of chlorine gas? So we're going to need to look at the coefficients here. We have 2 moles of phosphorus, 3 moles of chlorine gas, and 2 moles of phosphorus trichloride. We start out with chlorine gas. We have 3 moles over 2 moles, and we end up with 30.0 moles of phosphorus trichloride. How many moles of oxygen are required to form 15 moles of calcium oxide? So let's just jump here. So we start out with 15 moles of calcium. That moved a little bit. I apologize. We have 2 moles of calcium and 1 mole of oxygen. The moles of calcium cancel out, and we end up with 7.5 moles of oxygen. How many grams of calcium oxide can form from 2.5 moles of calcium? So we start with 2.5 moles of calcium. We have 2 moles of calcium. 2 moles of calcium oxide is over that. We then use the molar mass for calcium oxide, and the moles will cancel out, leaving us in grams of calcium oxide, which is 140. And there should be a period here to represent 3 sig figs, because this is 3 sig figs. There should be a period here, or decimal point, sorry. So technically that's wrong because that's only 2 sig figs. So if I had caught that, I would put a decimal here and here to correct that. Okay, so we have a problem here. If 40 moles of boron react in this way, how many moles of fluoride are consumed? How many moles of boron are required to produce 850.3 grams of boron trifluoride? So let's take a look here. If we have 40 moles of boron and it wants to know how many moles of fluoride are consumed by these two reacting, we have 2 moles of boron underneath, 3 moles of fluoride on top, and 60 moles of fluoride are consumed. How many moles of boron are required to produce 850 grams of boron trifluoride? So we use this and work backwards in a sense. So we have 815.3 grams of boron trifluoride, the molar mass for that, and then the mole ratio. And this answer has to be in moles of boron. So we have 2 moles of boron trifluoride, 2 moles of boron, which technically these cancel out. And it is 12.02 moles of boron, and that is 4 sig figs. You plan to run a reaction using 200 grams of tin and need to know how many grams of tin chloride will form. What steps are necessary for this calculation? So this is pretty much not asking you to solve it, but asking for the steps of it. So if we're starting with grams of one reactant and it's asking for grams of one of the products. So in this case, you're going to start with grams of tin to moles of tin. We don't work in grams. You have to get it out of grams, regardless of the problem. 99% of the time, 99.99% of the time, you've got to get it into moles. Then we go to moles of our reactant to a mole ratio of the product that we're interested in to grams of that using molar mass. So it's going to be C. When heated with the Bunsen burner, magnesium chloride decomposes to magnesium oxide and CO2. If 5.24 grams are heated in this manner, how many grams of magnesium oxide can form? Did we do this one? I feel like we did this one. It doesn't matter. 5.24 grams of magnesium carbonate. We use the molar mass of magnesium carbonate. We have a 1-to-1 ratio. So there's 1-to-1. We're now at magnesium oxide. We use the molar mass of magnesium oxide. And we have 2.51 grams of magnesium oxide.